applications of Markov chains. And let's just look at the back side of that single sheet handout. So this is the 4.9. Anybody need a 4.9? Oh, there you are. Hey, Victoria, welcome back. Hey. And we're going to do this exercise. Let P equal 0.2, 0.8, 0.6, 0.4, which is the stochastic matrix from the breakfast example. And I'm asking you to find a steady state vector for P. So I might ask this on our exam on Friday. A lot of the steps are things you already know how to do, but there are some aspects of this that are different. So watch as we go through. Don't snooze off. And so we need to find a vector V, which is going to be in R2, since this is a 2 by 2 matrix, such that PV equals V, and V is a probability vector. What does it mean to be a probability vector? That's one thing you gotta know. Yeah, the entries got to add up to 1, and they got to be positive. So no negative entries. It could be 0 for some. So the columns of a stochastic matrix are probability vectors. 0.8 or 0.2 plus 0.8 is 1. 0.6 plus 0.4 is 1. Okay. And there's a standard process for doing what we're about to do right here. So we're going to take this equation, and we can write it as PV minus V equals 0 vector. And we want to be able to factor out a V, but to factor out a V, we need a matrix times V, and we can write it as I2 times V. I'm just going to write I times V, even though it's understood it's a 2 by 2 identity matrix. So P could possibly be 3 by 3, 4 by 4. P has to be a square matrix. A stochastic matrix has to be square. So it would just be the appropriate identity matrix here. And we can factor out a V and solve this homogeneous equation. So what is P minus I? That's going to be 0.2, 0.8, 0.6, 0.4 minus 1001. And what you see happen here is what's always going to happen with a stochastic matrix. 0.2 times 0.1 is negative 0.8. Then we have 0.6. Then we have 0.8. and then we get negative 0.6. So notice how these entries, we have just positive and negative values of the same thing. I guess for the record, I'll write augmented matrix, so you all know the next few steps. Negative 0.8, 0.8, 0.6, negative 0.600, and we're going to reduce. And at least in this 2 by 2 situation, what's going to happen is I think you can see we can add the first row to the second. So leave the first row alone for now. And that second row is just going to become 0, 0, 0 right off the bat. And now I'm going to get a 1 in that first pivot position. So I'll divide through that first row. I wanted to get the zeros first, but now I'm going to divide through that first row by negative 0.8. So that's to get a 1 in this position. And 0.6 divided by negative 0.8 is negative 3/4. And so our general solution x, which is just x1, x2, is going to look like what? Is going to look like x2 is free, right? And x1 is going to be 3/4 x2. Now, normally we would stop there, right? We have a one-dimensional null space. But here's the one thing that's a little different. So don't mess up on the test, because I don't want to have to take points off when you do this. We got to find a probability vector. So there are many solutions to that equation, all possible values of x2, but we need a solution with the entries 3/4 x2 plus x2 equal to 1. That's to get a probability vector. So do you see where I'm getting this from? I'm just taking the entries in this form. I'm just saying x1 plus x2 has to add up to 1. But I plucked it out of the form where we had just one variable. So we can solve for x2. Does that make sense? And so I have 1 plus 3/4, 4, 5, 6, 7/4 x2 equals 1. So x2 is going to be 4/7. Finish it up over here. I guess we don't need x1. We can just say x, which was 3/4 x2 is going to be 3/4 times 4/7. 4/7, which is 3/7 4/7. That's the answer. There's only one probability vector. So there is only one probability vector solution. It's one particular solution. And I guess if I were any kind of respectable mathematician, I would know in my head the decimal form of 3/7 and 1/7. But just it's worth noting down here. Go around for ourselves. 3/7 as a decimal is approximately, because it has an infinite decimal expansion, repeating expansion point, 0.42857, 0.57143. And that's worth noting, because that looks like what we were approaching on Friday when I finally got the problem written down correctly. So this looks like the limiting value from last time. And it is. And what is supposed to be interesting about this, and I think is really interesting, is that we approach that same limiting value no matter what the initial condition was. So when I finally got things, when you guys finally helped me get things organized on Friday, we looked at two different starting situations, two different initial states, and they both led, in the limit, they both approached this same final result, which is what the one interpretation of what this steady state vector means. It's what we would approach no matter what the initial condition was. All right. Okay. Questions about doing that? Yeah, Ed?
When you were doing all this stuff, and I get the P equals V, Q minus IV equals 0, and we're looking for the null solution, why not just add one more row to the matrix and add that last equation 1, 1, 1? X1 plus X2 has to equal 1. Just row reduce the whole thing. Once you get there in one step, just another way to do it.
Yeah, I mean, it kind of takes it out of the universe of the original problem, but I think that would be okay. But so the original application I don't think that would make sense in, right? When you think about what is the eggs and no eggs business of, right, of this. But it is sort of like we're just adding one more equation to our system. So you could create a larger system. But personally, I would prefer not to do that. Because it takes us outside the original meaning of the problem, I think. Okay. Anybody else want to? So there's a little bit more on that handout. And we're only going to talk about this. There are no problems that deal with this, but I just want to mention it. There's something called a regular stochastic matrix. A regular stochastic matrix has all positive entries in p to the k power for some power k of p. So I'm just going to refer to the examples that are in the handout. I say our example p that we started out with, this is a regular stochastic matrix because p to the first power has no zero entries. By all positive entries, we mean no zero entries for some power p to the k. And it could be p, which is p to the first power, which is true for our example. It started out as a regular, in regular form. The second example there, that identity matrix, this is a stochastic matrix, 1, 0, 0, 1, but it's not regular because there's no power of this that make the zeros go away. And it's okay if you say, I'm not going to worry about that. There's a third example there that I made up. That's a 3 by 3 stochastic matrix. Notice that P does have a 0 in one of the entries, right? And I used Desmos to help me figure out what P squared was, because those numbers are so messy. I would have had a hard time figuring that out. And notice that when you square P, there are no 0 entries. So I just wrote down the result for P times P. That's what P squared is. And I believe once you get no 0 entries, higher powers, all higher powers will not have a 0 entry. Yeah?
0 doesn't count as a positive number?
Right. 0 is not a positive number. So when I say has all positive entries, this is what I'm really saying. That's why I paraphrased it on the board. Because it already can't have negative number entries. So I realized that statement on the handout, P to the K has all positive entries, is sort of sleazy statement, right? We already know they can't be negative. So what we're really saying is it can't have any zeros. I think I copied that statement out of the textbook. That was a textbook's definition.
So then a matrix is, it's either regular or stochastic matrix is either regular or not regular, right? It can't like as K increases, for example, can it become? I mean, well, I guess it's the same.
I'm pretty sure, and I can't 100% swear to it, but I'm pretty sure once there's a regular form of P to the K, once there's no 0 entries, higher powers will not have 0 entries. And I don't think that's obvious why, but once the zeros go away, they stay away. I'm pretty sure that's true. I'm not 100% sure that's true.
So for example 3, do we say that P to the first power is not regular and P to the subsequent powers?
No, P is regular. I mean, if some power has all positive entries, non-zero entries, the original matrix is said to be regular. So even though I don't know, in our mind, we kind of say it gets to be regular, but really the original matrix is regular. So for all these stochastic matrices, there are some where eventually the zeros go away, and there are some where no matter what power you take, and this is sort of the easiest example, the identity matrix, because all powers of the identity matrix are the identity matrix, so all powers will still have 0. So that's never, it's not regular. It's never going to happen with the identity. And so there's a theorem there, I just state this for information. If P is a regular stochastic matrix, then P has a unique steady state vector. Also, for any initial state, if xk plus 1 equals p x sub k, which is just how we defined our Markov chain, then the xk vectors approach the steady state vector as k approaches infinity, which is what we observed in our example. So we're not going to study this any deeper than that. But what happens is non-regular stochastic matrix can actually have more than one steady state vector, and I believe they can have possibly no steady state vector. There could possibly be no limiting value. So that's just extra. So the getting to here on a problem is what you need to know. Okay. And then we're done with that. So what should we do? We could start review. Well, okay, I know what I want to do. We're going to do a little bit of review, and maybe I'll start chapter 5 after that, and then we'll do more review on Wednesday. But I wanted to talk about one particular problem in our review from the test I gave last semester, and everyone hated this problem. And I thought, it's one of those things where the teacher thinks everybody can do it, right? Like, believe it or not, we try to put problems on tests that we think you can all do, and then nobody can do it, and the teacher's like, what did I do wrong? So I thought it would be worth going over that. And maybe before I give you this problem, let's just take a look at that summary sheet that you guys have. So you should all have one of these. Victor came in a little late. So this is just my personal summary of the Chapter 4 material, because I think a lot of those sections are related to each other. It's not like you can just break it down into 4.1 separate, each section separate all the way through 4.7 and 4.9. The summary does not talk about Markov chains, so I put a little blurb cloud up in the corner. So you are responsible for a Markov chain problem. That's not listed here except up in this little corner cloud. So verify that a subset is a vector space or isn't, or I'm sorry, verify that a subset of a vector space is or isn't a subspace. That's something you need to know how to do. Either check the 3 properties or use there's a possible shortcut. Use the fact that the span of a set of vectors is always a subspace. To me, those are the 2 main ways we can show that a subset is a subspace. I will not ask you to verify that something is a vector space using that long list of defining properties. We didn't do homework on that. Vector space examples are N, CAB. What does CAB mean? Continuous functions on the interval AB. So for a particular example, you would need numbers filled in for A and B. We've looked at continuous functions on the closed interval from 0 to 1. There's what we call real valued functions. Continuous on the closed interval from A to B. And that P sub n is a set of polynomials of degree less than or equal to n. Determine if a set of vectors is linearly independent, if a set of vectors spans a vector space or subspace, or is a basis of a space or subspace. Determine if a vector is in the null space, column space, or row space of a matrix, or is in the span of a set of vectors. Find a basis and find the dimension for null A, column A, row A, span of a set of vectors where A is an n by n matrix. Change of coordinates of a vector from one basis to another. Find a change of basis matrix and find its inverse. And then you will have to interpret rank. Rank of an m by n matrix is the dimension of the column space, which is equal to the dimension of the row space. And you want to make sure you know that formula. Rank A plus the dimension of null A equals n. So think between now and Wednesday, think it like you can say, are we going to have to know this or are we going to have to know that, right? If it's okay to ask me. All right, let me give us a problem now. So possible test question. Let P P2 denote the vector space of polynomials of degree less than or equal to 2. So we're familiar with that notation. Consider the linear transformation I'm going to call T from P2 to R3 defined as follows. T of P equals P of 0, P of 1, P of 2. Describe the kernel, that is the null space of T. And then I had said on the test, you don't need to verify that T is a linear transformation. So that probably got everybody even more confused. I was trying not to be confusing. I'm sure people were like, huh? What? So you have to describe the set of polynomials P of T such that what? T of P of T is the 0 vector. Is 0, 0. Kernel of T So is this just totally mysterious? So if this guy is 0, P of 0 is 0, P of 1 is 0, and P of 2 is 0, right? We want to describe all so what's a typical element of P2 is P of T equals, now you can choose the variables here. You could use ABC, you could use subscripts, you could say A0 plus A1t plus A2t squared, or write that in reverse order. I don't know why I put the constant first. Does our book, I can't remember if our book usually writes it this way. If you don't like subscripts, you could just use 3 separate variables for these coefficients. I know in my solution sheet for the class, I wrote A, B, and C instead of A2, A1, A0. I wrote the subscripts now because I think maybe you guys are more used to looking at those examples in the textbook where they tend to label the coefficients with subscripts. So that's a typical element of P2. So if P is in the kernel, T of P is the 0 vector. So do you see why I'm saying we're going to get 0, 0, 0? That's why I'm saying P of 0 is 0, P of 1 is 0, P of 2 of 0. P of 0 for any polynomial is what? It's got to be the constant, right? A0, because if you plug in 0 for t, you get A0. P of 1 is going to be what happens when you plug in 1 for t. You're going to get A2 plus A1 plus A0. P of 2 gets a little bit more complicated, right? Because we got to square what we plug in. So that's 4A2 plus 2A1 plus A0. And so we're saying find those elements. P is in the kernel of T if P of 0 equals 0. Well, that's if A0 is equal to 0. And P of 1 equals 0. That means A2 plus A1 plus A0 equals 0. And P of 2 equals 0. 4A2 plus 2A1 plus A0 equals 0. Solve for A0, A1, and A2. What are all possibilities here? Of course, A0 is already 0. Yeah, they could all be 0, right? The kernel could just be the 0 vector, right? So we know A0 has to be 0. So that's going to be gone and gone from those equations, right? A2 plus A1 is 0. 4A2 plus 2A1 is 0. You could just play with the algebra. A2 is equal to negative A1. So this equation becomes 4 times negative A1 plus 2A1 equals 0. Negative 2A1 equals 0. A1 equals 0, which implies A2 equals 0. So there's only one solution. A0 equals 0. A1 equals 0. A2 equals 0. So the only solution is P of t equals the zero polynomial. And in fact, that's got to be a one-to-one linear transformation then. No? Nobody's. Well, I guess I can't put that one on a test then, because I just did it for you. So that's a little bit of an excursion into that thinking of an abstract linear transformation. Some people turned it into a matrix problem.
Or like solving the system.
Yeah, like you could say, what would that do to your standard basis, sort of? Your 1t squared. Oh, yeah. I mean, you can also turn this into, let's not talk about this. So you don't have to do the algebra. If you prefer to set up a matrix, I mean, I don't even have to write this down, right? You just have a system of three equations. And we just have to decide what order we're going to write this A0, A1, A2 in. So let's see, I think it's like 1, 0, 0, equal 0, 0, 0. This will correspond to A0 equals 0 equation. The A1 plus A2 plus A0 would be like a row equals 0. And my third equation is, what was it? It was 4A2, 2A1, 1A0, so 1, 2, 4 from the way I wrote things here. And again, you can just show this matrix is invertible, etc. Okay, that's enough talking about this. So the answer, just to sum it up here, is the kernel of T consists of just one polynomial, P of T equals 0, i.e. 0t squared plus 0t plus 0. I feel like I must have got that out of the homework somewhere. Yeah, wasn't there something like that on the homework? Okay, let's try something else. I didn't think that was so scary. I don't know. But everybody really... To me, it was just a question of writing down what it was saying and then seeing that you ended up with some equations involving the coefficients of a polynomial that could be in that kernel. Okay. like I have to talk about something you're going to be happier with here. So let G equal xy such that y equals x plus 1, x, y in R. Let H be 3a plus b, 0, a minus 5b, such that a and b are in R, real numbers. So this was one problem on the test last time. Is G a subspace of R2? Y? And B, is H a subspace of R3 and Y? So I'll wait a little bit. So this you should feel good about. It's really two problems in one. They're totally independent of each other. There's no connection at all between G and H. Just I combined them into one test problem. So geometrically, G, if we visualize as points in R2, we're just looking at all the points on a line, right? On the line y equals x plus 1. That's really all that's saying. All the points on the line y equals x plus 1. I think, should we? Let democracy rule. G a subspace? The first one, A? No, with confidence, right? No? The answer is no for G. It's no. I think the easiest way for me to think of it is to rewrite that xy as x plus 1 and you can actually think of that as x times 1, 1 plus the vector 0, 1 if we go to that sort